Hello everyone and welcome to another lecture on probability. In this lecture we will continue with the continuous random variables, and in particular we will take a look at some standard random variable examples and study their properties. In particular we will take a look at the uniform distribution, the exponential distribution and the normal distribution. These are very common continuous random variable distributions, which we will give the probability density function of these distributions, and we will see some nice properties that these distributions have. The first is an example which you have seen already several times, which is the uniform distribution. We will often write x is distributed as uniform of a comma b. You might see it written this way, where this wavy symbol indicates distributed as. This particular statement is to be read as x is the random variable x is distributed as uniform a comma b. So what does that mean? Well, that means the density function fx of x is simply equal to 1 by b minus a if x belongs to a to b and 0 otherwise. This is the density function associated with this distribution. We have already seen this several times, but I am just making it giving a notation of uniform a comma b. And we also know what the expectation and variance of this random variable are. We will just write that down again for completeness. The expected value of this random variable is simply a plus b by 2, and the variance of this random variable is equal to b minus a the whole squared by 12. We derived both these things when we introduced expectation and variance, but it is very easy to derive these from first principles again if you want. So that is all we have for uniform distribution. We will move on to the next distribution, which is called the exponential distribution. The exponential distribution is extremely analogous to the geometric distribution that we saw for the case of discrete random variables. We will first give the notation for that. So we will say x is distributed as exponential with parameter lambda. If that is the case, what is the density function? Well, fx of x is equal to lambda e power minus lambda x if x is greater than or equal to 0 and 0 otherwise. So this is a positive random variable. So if you plotted the density function of this random variable, this is what it would look like. It would start at 0, and before 0 it is going to be 0. Fx of x is going to decay exponentially. So lambda e power minus lambda x. The first question you should ask for such a definition is that, is it a valid density at all? So for this to be valid density, this must integrate to 1. Is that true? Let us do a quick check of that. Let us do a quick check. Integral 0 to infinity lambda e power minus lambda x dx lambda minus 1 by lambda e power minus lambda x within the range 0 to infinity. Well, this is clearly equal to lambda into 1 by lambda, this is equal to 1. So we know that this, if you integrate the density function from 0 to 1, you get back 1, which means that the area under the curve for this curve is equal to 1. So this is a valid density function, okay, right. But can you get the cumulative distribution function of this random variable as well? You can, and it is a pretty nice function. The CDF fx of x is simply probability of x less than or equal to x, which is indeed exactly equal to integral 0 to x fx of u du, right. So this u is a dummy variable, so it does not matter much, and it is straightforward to show that this is equal to 1 minus e power minus lambda x. If x is greater than 0, if x less than 0, this is going to be equal to 0. Fx, the the probability of x less than or equal to any negative number is going to be 0 because exponential is a positive random variable. So, probability of x less than or equal to x for negative x is going to be 0, and as for positive x is going to be 1 minus e power minus lambda x. So, for that is for x equal to 0 you start at 0, and as x increases this slowly increases and it never really hits 1, but it asymptotes to 1. Right. So, that is this 1 here is an asymptote here, it touches the CDF at infinity. Once again you can see that the left end of this curve is 0, the right end of this curve is infinity, sorry, right end of this curve is 1. Right. At the left end fx of minus infinity is 0 and fx of plus infinity is equal to 1. So, this is a basic property of the CDF and this indeed satisfies that. So, why am I saying the exponential random variable is similar to the geometric random variable? Because this is has very similar properties and it also is used for modeling a very similar object. You saw that the geometric random variable is very useful for modeling the number of tries before you succeed. That was the most standard way you would arrive at a geometric random variable. Similarly, the most common uses for exponential random variable is also time till failure. For example, a typical example for an exponential random variable might be you might say that the running time of this electric bulb is exponentially distributed with lambda equal to 0.5 per year, right. So, well, the unit will come to that. So, you might say exponential per, what does that mean? That means that your the time with which this electric bulb is going to function normally is a random variable. It might fail in the first hour itself, or it might run for 2 years, or it might change anything, right. So, the manufacturer needs to know the random variable, needs to know the distribution of the running time of this particular product, so that based on that he or she the manufacturer can give a warranty, right. So, you can say, well, if I know that for sure this product is going to last for 2 years, I can safely give out a 2-year warranty and say that if your product breaks less than 2 years I am going to give a replacement. The manufacturer can say that with confidence because he or she knows that it most likely is going to last 2 years. This exponential random variable is pretty useful for modeling such kind of objects, which is very similar to the case where exponential random variable is used for modeling time. The same way the geometric random variable is used for modeling the number of tries. The number of tries you could view it as an analog of time, where the number of tries is similar to time, right. Okay. Right. So, this exponential distribution has certain nice properties. One of the most important properties is what is called as memorylessness. What does that mean? Let us well, we will just say what the property means and we will show this satisfies that property. This is what the property says: the probability of x greater than or equal to a given x greater than or equal to b, let us say a is greater than b, right, is equal to probability of x greater than or equal to a minus b. Right. So, let us try to interpret this statement. This says that let us say b is 1 year and a is 3 years, right. What you are saying is, what is the probability that this electric bulb is going to last more than 3 years given that it has lasted for 1 year, right. That is the situation here. You know that this electric bulb has lasted for 1 year, you want to know the probability that this electric bulb is going to last for more than 3 years. Right. That is what the memoryless property says, that this is exactly equal to the probability that this electric bulb would have lasted for more than 2 years. Right. So, a minus b is 3 minus 1, which is 2 years. So, this is a natural property that most components in the real world, because where each component can fail or succeed with some due to some random event, in that case exponential satisfies this property, and this is a very natural notion, right. So, if given that if a product can be in just 2 stages, one is it can completely broken down and second running perfectly, right. If that is the case, if it is running perfectly for 1 year and you want to ask the probability that it is going to last for a total of more than 3 years, it is exactly equal to the probability that from the beginning it would have lasted for 2 years. That is what the memoryless property says. Let us try to derive this, right. What is the left hand side here? Is probability of x greater than or equal to a and x greater than or equal to b divided by probability of x greater than or equal to b. We have already said a to be greater than b. So, probability of x greater than or equal to a and x greater than or equal to b is exactly the same as probability of x greater than or equal to a. By probability of x greater than or equal to b. Probability of x greater than or equal to a is exactly equal to 1 minus probability of x less than or equal to a, which is 1 minus e power minus lambda x. So, we can say this is equal to e power minus lambda a and denominator is e power minus lambda b. Now, we can see why you get a minus b here, this is equal to e power minus lambda into a minus b. This is exactly equal to the probability that x is greater than or equal to a minus b. So, this is the memoryless property of an exponential random variable. So, you will see a very similar property like this hold also for geometric random variables, but geometric is discrete, exponential is continuous, that is the only difference, right. So, okay, so that is the memoryless property, but before we go to something else, let us first get the expectation of this particular random variable. What is the expected value of, let us say if x is distributed as exponential of lambda, what is the expected value of this random variable? Well, it is equal to integral 0 to infinity x into e power x lambda e power minus lambda x dx. This looks like a complicated integration, but you know exactly what tool to use for these kind of integrals, that is the integration by parts that you might have seen in your school. Let us go ahead and do that. What does integration by parts tell you? It says that integral u dv is equal to uv minus integral v du, right. So, now in this particular case let us set u to be equal to x, set u to be equal to x, which means that du is going to be equal to dx, and we will set dv to be equal to e power minus lambda x dx. So, in which case v would be equal to minus 1 by lambda e power minus lambda x dx, right. So, now we can do the integration x e power minus lambda x dx is equal to uv, u is equal to x, v is minus 1 by lambda e power minus lambda x. So, that would be minus x by lambda e power minus lambda x. The integral limits are between 0 to infinity, within limit 0 to infinity, minus integral v du, v would be minus 1 by lambda e power minus lambda x. So, the minus becomes a plus here, 1 by lambda e power minus lambda x, du is exactly equal to dx. So, for v you would not have a dx, I am sorry for that. So, v du. Now, let us do this integration. The first term would be 0. Why is that? Because if substitute infinity, it looks like infinity into something, but e power minus lambda x is it's much closer to 0 than x, and if x keeps on increasing, x e power minus lambda x goes to 0, because e power minus lambda x is much closer to 0 than x is to infinity. So, x e power minus lambda x as the limit x goes to infinity is 0, and 0 e power minus lambda 0 is also 0. So, this term is entirely equal to 0. What about the term on the second term here, that is plus, right. So, that is 1 by lambda e power minus lambda x, 0 plus 1 by lambda into e power minus lambda x, which is going to be equal to minus 1 by lambda e power minus lambda x within the range of 0 to infinity. So you get this is you already have 1 by lambda here and minus 1 by lambda e power minus lambda x in the range of 0 to infinity, which is equal to 1 by lambda e power minus lambda x in the range of infinity to 0, which would be equal to 1 by lambda squared. So what we have is integral 0 to infinity x e power minus lambda x is equal to 1 by lambda squared, but what would we want? We want this integration, which is simply lambda times this integration. So 1 by lambda square into lambda, which is equal to 1 by lambda, right. So that means that Ex is equal to 1 by lambda. You can see the similarities to the geometric random variable coming here again. So you saw that for the expectation of a geometric random variable was 1 by p, here you have 1 by lambda, right. So that is similar here. If you have a very small lambda, which means then you have Ex to be quite large. So lambda, the unit of lambda, for example in the case of bulb failure experiment, would be per year, right. So if you have lambda of let us say 0.5 per year, then you expect this bulb to last for 2 years. Right. So that is the exponential expectation of the exponential random variable. You can derive the variance also using the same way, using integration by parts, but the variance is not very important right now, right. So the expected value of an exponential random variable is nicely equal to 1 by lambda. Right. Let us go ahead and x is distributed as exponential with parameter lambda, right. And let us say y is distributed as exponential with parameter let us say tau, and x and we will say x and y are independent. Right. Now we define z to be equal to minimum of x comma y. Then what is the distribution? What is z? Right? What we will show is that z is distributed, we will show that z is distributed as exponential with parameter given by lambda plus tau. This is particularly nice because you can interpret this x and y. Let us say you have a CPU, so let us say you have a laptop and there are only 2 components, let us say CPU and RAM, right. Let us say the failure time of the CPU is exponential with 1 by 4 per year, 0.25 per year, and let us say y, the RAM is a failure, the failure time of the RAM is exponential with let us say another 1 by 4 per year, right. So effectively individually you expect your RAM to last 4 years and CPU to last 4 years, but you give a warranty to let us say the laptop as a whole, then how long should you give the warranty for? Let us say what you do is you just replace the warranty, you just replace the laptop as a whole. If that is the case, if you have 2 components and what matters is even if one of them fails, you have to let us say junk the entire thing. If that is the case, z would essentially correspond to the failure time of the laptop as a whole. The min of if whenever the first of these 2 things fail, the entire thing fails, right. So z is equal to min of x comma y. What this particular simple theorem states is that z, the failure rate of z is also an exponential random variable with lambda plus tau, and that is natural in the sense that if you have x to be the failure rate of let us say 0.25 per year and y to be let us say 0.25 per year also, then z would be 0.5 per year. So which means that the expected value of z is going to be equal to 2, right. That is not particularly that is intuitively obvious, but we have to prove this still. How do we prove that z is distributed as exponential of lambda plus tau when z is equal to min of x comma y, where x and y are independent? We already have the formula for the minimum of how do we get the density of the minimum of 2 independent random variables, and based on that we have f, the CDF of z, fz of z is simply equal to 1 minus fx of z into 1 minus fy of z. This we derived previously for general minimum of 2 random variables. We can substitute that here. This is 1 minus fx of z is already 1 minus e power minus lambda z, 1 minus that will simply be e power minus lambda z, and this would be e power minus tau z. You can say this is equal to 1 minus e power minus lambda plus tau z. So, if z is greater than or equal to 0, this thing is if z is greater than or equal to 0. If z is less than 0, then it is clearly 0, right, because your CDF of z cannot z cannot take negative value. So, f z of z if z is less than 0 is clearly 0. Now, what is 1 minus e power minus lambda plus tau z? That is exactly equal to which means that the density of z f z of z is equal to 0 if z less than 0 and lambda plus tau into e power minus lambda plus tau z otherwise. So, this is exactly the density of an exponential random variable with parameter lambda plus tau. So, this is one way you can see how exponential random variable is a very natural way for modeling time of failure. Right. So, now we will move to the next example, which is the normal distribution. The normal distribution is something which you might have seen already in your school and it has a very characteristic bell curve, right. So, the density of the normal distribution. So, we will say Z is distributed as normal, standard normal or normal with parameters 0 and 1. We will say what the general parameters are pretty soon, but in the case of the standard normal, which corresponds to saying that Z is distributed as normal with parameters 0 and 1, we will say that f the density of Z f z of Z is equal to 1 by square root of 2 pi x of minus z squared by 2. This is the density function of the standard normal random variable. And if you plotted the density function, you would have this characteristic bell shaped curve. You can clearly see it is centered around 0 and it decays in this way as you move either in the negative direction or in the positive direction. So, Z can take both positive and negative values. So, this is the density function of the standard normal. Okay. Right. So, first question you should immediately ask is this a valid density? Right. How do you know this is a valid density? Well, you have to integrate this from minus infinity to infinity and check if it is a valid density. Right. So, now for that let us go ahead and do this. Right. Let us define some integral here a to be equal to integral minus infinity to infinity e power minus z squared by 2 dz. Right. Let us use x here, it will be easy for us to use x here. How do you essentially we want this for if our density here was a valid density, if you integrated this from minus infinity to infinity, this you should get root 2 pi. Right. How would you get square root of 2 pi? Well, let us try and do this integration. Right. So, in fact this integration is quite hard to do, but there is a small trick that we can do to make this a much easier integration. Right. Let us define, instead of doing a, let us do a squared. Right. We will say a squared is equal to integral minus infinity to infinity e power minus x squared by 2 dx into integral minus infinity to infinity e power minus y squared by 2 dy. Why am I doing this? Well, y is a dummy variable, so it does not matter here. This is also equal to a, this is also equal to a, but we can bring both these together into a single integral. We will call integral minus infinity to infinity e power minus x squared plus y squared by 2 dx dy. How does this actually help us? The reason this helps us is because we can do a change of variable here. Right. You can view this as integrating e power minus x squared plus y squared by 2 over the entire xy plane. Right. So, now we can use a Cartesian to polar transformation where we will define r and a theta as follows, where x is equal to r cos theta and y is equal to r sin theta. The standard polar coordinate transformation. So, integrating over x and the entire xy plane exactly corresponds to integrating over r from 0 to infinity and theta from 0 to 2 pi. Of course, dx dy has to do a change of variable rule. Dx dy we know corresponds to r dr d theta, which is also a standard integration trick, integration rate of change of variable that you might have seen. So, you vary r from the range 0 to infinity and theta from the range 0 to 2 pi. But why do we do that? Well, that helps us because x squared plus y squared is exactly equal to r squared. So, this becomes e power minus r squared by 2 and dx dy simply becomes r dr d theta. The main advantage of this particular change of variable is that now you have r squared and r dr. So, now you can do another change of variable where r squared by 2 becomes the variable and r dr we can get it out, right. Let us do that integration. Integral 0 to a squared is equal to integral 0 to infinity integral 0 to 2 pi e power minus r squared by 2 r dr d theta. So, you can take the d theta integration outside. So, it is integral 0 to 2 pi d theta integral 0 to infinity where instead of r squared by 2 let us define u to be equal to r squared by 2, right. So, if you do that the limit of u does not change, it is still 0 to infinity, but du is exactly equal to r dr. So, you have e power minus u du. And this integration is pretty easy, you can do that and you will get back 1 and this integration is also easy, is equal to 2 pi. So, we get a squared is equal to 2 pi, which means that a is equal to square root of 2 pi, which means that our density is a valid density because if you integrate this from minus infinity to infinity you get square root of 2 pi. So, that is why you have this 1 by square root 2 pi to cancel it out. So, now we have that if you integrate this from minus infinity to infinity you get the value of 1, which means that this is a valid density. Okay, right. So, this settles that this is a valid density. Why are we actually bothering so much about this particular distribution? Because you will soon see that this is a very commonly occurring distribution in nature, and one of the main reasons is what is called the central limit theorem, which we will soon see that practically all situations where multiple effects are essentially added together and you see an effect, you can expect the effect to be a normal distribution. There is another name for the normal distribution which is called the Gaussian distribution. It is also called the Gaussian, right. So, we will see the central limit theorem soon, but there are several practical examples of normal distribution. For example, let us say you are measuring current in a wire when there is no voltage difference, right. Let us say you have a very accurate ammeter and you are measuring the current in a wire, what you are seeing is just noise and that noise is normal distributed or Gaussian distributed and so on. You will see several examples in practice where things are normally distributed. Right. So, we saw Z distributed as normal 0 1, right. But what are these two parameters 0 and 1, right. We will see that soon. Now, let us define x to be equal to sigma times z plus mu. Right. So, sigma is a scalar constant and mu is also a scalar constant, right. So, x is equal to sigma z plus mu. Now, what can we, let us say z is distributed as normal 0 1. What can we say about the density of x, right. So, fx of x is equal to what, that is the question, right. You can use our change of variable rule because this happens to be an invertible transform, right. So, fx of, if x equal to sigma z plus mu, z equal to x minus mu by sigma. So, fx of x is simply equal to fz of x minus mu by sigma, and then you have the Jacobian of this transformation. So, this is just a 1 to 1 thing, but you can still do the Jacobian of this, which happens to be just equal to 1 by sigma. So, what is fz of x minus mu by sigma? We can just substitute that here. This is 1 by square root of 2 pi x puff minus half x minus mu by sigma the whole square. Right. So, I have just replaced z by x minus mu by sigma. So, this is x minus mu by sigma the whole square, and then you have a sigma. So, put these together and you get the standard definition of a normal distribution, that is fx of x is equal to 1 by sigma square root of 2 pi x puff minus 1 by 2 x minus mu the whole squared by sigma square. And we will just say x is distributed as normal with mu and sigma squared. So, now we get the general normal random variable instead of just 0 and 1, where mu and sigma squared we get back, right. Okay. So, what is the expected value of x? You could in principle just integrate this over minus infinity to infinity and get the answer, but you do not need to. Why? Because x itself was distributed as sigma z plus mu, right. So, expected value of x is simply equal to expected value of sigma z plus mu, and by linearity of expectation we have this is equal to mu plus sigma into expected value of z. What is expected value of z? This is pretty easy because z is actually a symmetric random variable around 0. So, expected value of z is equal to 0. So, this is equal to mu. So, if you have a normal mu sigma squared random variable distribution, the mean is mu. Okay. What about the variance? Right. What about the variance of x? Well, you can use the same sigma z plus mu effect here to get this is equal to sigma squared into variance of z. Right. What is variance of z? Variance of z you have to do an integration, which is you have to integrate z x squared into e power minus x squared by 2 within the range of minus infinity to infinity. But what you will get is variance of z is actually equal to 1, that is a single integration. I am not going to do that, but that is equal to 1. So, this is equal to sigma squared. So, variance of x is equal to sigma squared and expected value of x is equal to mu. So, that is why you will often see these mu and sigma squared be referred to as the mean parameter and the variance parameter, right. So, mu is exactly equal to the mean and sigma squared is exactly equal to the variance. The mean and expectation we will be using interchangeably as I mentioned earlier. So, this is called mu is the mean parameter and sigma squared is the variance parameter. Right. So, with that we are done with the standard distributions that we will see, which form the building blocks for more complex distributions.